diving into the world of cybersecurity reveals fascinating, and at times, unsettling prospects. Today, our focus is on a topic relevant to every internet user, from schoolchildren to the heads of major corporations: phishing attacks. While many might believe they are well acquainted with this concept, phishing methods are constantly evolving, becoming increasingly sophisticated and unpredictable. Phishing is a deceitful type of attack based on social engineering, primarily aimed at stealing personal data, including logins, passwords, and credit card numbers. Attackers, skillfully disguised as trusted organizations or individuals, trick victims into opening emails, messenger messages, or SMS. Then, using various psychological tactics, they persuade recipients to click on malicious links. These links can lead to the installation of spyware, system lockdown with ransom demands, or the disclosure of confidential information, all of which can have serious consequences. In the past, phishing emails were often identifiable by poor formatting and grammatical errors. They typically came from unknown senders and contained direct requests for banking details. But today, everything has changed. Modern phishing attacks are characterized by a high level of execution. Attackers create fake websites that are virtually indistinguishable from legitimate ones. They use personal information obtained from social media and skillfully manipulate news and events to create a sense of urgency and fear in the victim. For example, during tax season, one might receive a fake email from the tax service, or during a pandemic, a message disguised as medical advice. So, how can you protect yourself from these insidious attacks? First and foremost, exercise caution and skepticism toward any unsolicited messages, even if they appear to be from a reliable source. Never click on suspicious links without verifying them. Hover your mouse over a link to see its actual address. If it looks strange or raises doubts, it's best to refrain from clicking. Use strong and unique passwords for each account, and if possible, enable two-factor authentication. This adds an extra layer of protection to your data. Regularly update the software on your devices. Updates often contain security fixes that patch known vulnerabilities and protect against new threats. Finally, increase your awareness and share knowledge with loved ones. The more you know about phishing and other cyber threats, the better you can protect yourself and those around you. Remember, cybersecurity is a shared responsibility. Be vigilant, be cautious, and don't let attackers trick you. Mercury, the smallest planet in our solar system, is subjected to the most intense solar radiation. At its closest point to the Sun, known as perihelion, the Sun appears 3 times larger from Mercury's surface than it does from Earth, and its brightness is 7 times greater. Mercury's orbit is notable for its significant inclination of 7 degrees relative to the ecliptic plane, the largest among all planets in our system. Despite this, Mercury periodically passes between Earth and the Sun, delighting astronomers who, equipped with specialized instruments, bravely observe the solar disk. Mercury transits occur approximately once every 7 years, with the last one recorded in 2019. A small black dot against the vast, shining disk of the Sun serves as a vivid reminder of our star's grandeur. Mercury's orbit is a unique and hard-to-imagine phenomenon. Besides its inclination relative to the ecliptic plane, it also boasts the greatest eccentricity among all planets, meaning it has a pronounced elliptical shape. Completing an orbit around the Sun in just 88 Earth days, Mercury's elongated path brings it as close as 47 million kilometers to the Sun and as far as 70 million kilometers. While it is the fastest planet in its orbit, Mercury rotates relatively slowly on its axis. One rotation takes 59 Earth days. Thus, for every 2 full orbits around the Sun, Mercury completes 3 rotations on its axis, when viewed relative to the stars. However, this does not mean the Sun rises and sets 3 times in 2 Mercurian years. In fact, it happens only once. On Earth, we are accustomed to thinking that the Sun's movement across the sky is solely due to the planet's rotation on its axis. And while this is true, it's not the only factor. In reality, the Sun's apparent motion is also influenced by the planet's orbital movement around the Sun. We don't typically notice this because our planet rotates quite rapidly, but Mercury is a different story. For an observer on Mercury's surface, the Sun, like on Earth, moves from east to west, but it does so much more slowly due to the planet's leisurely axial rotation. The Sun's movement across the sky is significantly impacted by Mercury's orbital motion around the Sun. As a result, a single day on Mercury lasts twice as long as a Mercurian year, meaning it takes 2 local years, or 176 Earth days, for the Sun to fully illuminate the entire surface of the planet. The most interesting phenomena occur when Mercury is at perihelion, its closest point to the Sun. At this moment, an observer on the planet's surface might notice peculiar behavior from our star. The Sun's movement across the sky, usually from east to west, is suddenly disrupted. It appears to stop at some point, then begins to move in reverse, eastward, before returning to its normal westward motion. This is explained by the fact that as Mercury approaches perihelion, its orbital speed increases, and at a certain point, it matches the planet's rotational speed. At this precise moment, for an observer on Mercury, the Sun appears to freeze in the sky. The closer to perihelion, the faster the planet moves, and at some point, its orbital speed surpasses its rotational speed, causing the Sun to appear to move backward. Finally, after passing perihelion, the Sun's normal motion resumes as the rotational speed once again exceeds the planet's orbital speed. Interestingly, during this solar dance, there are locations on Mercury's equator where the Sun lingers for 2 to 3 Earth weeks. Given Mercury's proximity to the Sun at perihelion, the planet's surface can heat up to 430 degrees Celsius during this period. However, due to the lack of an atmosphere, heat is not transferred to the night side, so temperatures can drop to -180 degrees Celsius during the long, cold nights. Such an enormous temperature swing is not found on any other terrestrial planet. Nevertheless, Mercury is not as hot as Venus, where radiation can barely escape the planet, leading to its constant heating. The temperature difference on Mercury could have been even greater if the planet were tidally locked to the Sun. Interestingly, astronomers believed this to be the case until the 1960s, thinking one side of the planet always faced the Sun. However, thanks to the Arecibo Observatory, the presence of rotation was confirmed. Since Mercury completes several orbits around the Sun while Earth completes only one, Mercury overtakes Earth approximately 3 to 4 times a year. This creates an interesting optical illusion where the planet appears to move backward in the sky for about 3 weeks. Astronomers call this retrograde motion. The effect is quite interesting, but it's not worth believing claims that it somehow affects your life. Exploring Mercury is challenging not only with telescopes. Sending a probe to the planet also presents a difficult task. According to the European Space Agency, sending a mission to Pluto is easier than to Mercury because it requires less energy. The reason lies in Mercury's proximity to the Sun, deep within the star's gravitational field. If the goal of a space probe is not merely to fly past the planet while orbiting the Sun, but to enter orbit around Mercury, the spacecraft must constantly decelerate, overcoming the star's incredible gravity. This either requires a huge supply of fuel for engine braking or necessitates slowing down using the gravitational pull of other planets, specifically Earth, Venus, and Mercury itself. With the help of planets, spacecraft can not only accelerate but also decelerate and change trajectory. Several such flybys are required to slow down sufficiently before entering orbit around Mercury, which significantly increases the flight time to the planet. It's no surprise that only 3 spacecraft have thoroughly explored the surface of the closest planet to the Sun. The first was Mariner 10, which flew past Mercury in the 1970s while orbiting the Sun. Mariner flew near the planet 3 times and was able to image about 45% of its surface, also discovering a mysterious magnetic field for the first time. After a 30-year hiatus, a separate NASA mission called Messenger was launched to Mercury, with the goal of entering orbit around the planet. The mission's name is merely an acronym and has no relation to any messages. Launched in 2004, the spacecraft followed a complex route, using gravitational assistance from Venus and Mercury. In 2011, after 7 years of travel, it entered orbit around Mercury, and it is thanks to its 4-year mission that we have most of the information about the planet's surface and its internal composition. Mercury's surface resembles a lunar landscape, dotted with craters formed by meteorite and comet impacts. A colossal impact basin, named the Caloris Basin, stretches over 1,000 kilometers in diameter. It resulted from a collision with a giant asteroid in the early stages of the planet's formation. This crater, one of the largest in the solar system, dominates the Mercurian landscape. For context, the entire territory of Ukraine could fit within its boundaries. The force of the impact was so immense that it caused lava eruptions on the opposite side of the planet. Directly opposite the Caloris Basin lies an extensive region of hills and depressions known as the Weird Terrain. In 1975, researchers hypothesized that this terrain might have formed under the influence of shock waves generated by the asteroid impact. Spreading across the planet, these waves converged on the opposite side, where high stress in the crust led to its deformation. Within the Caloris Basin is the Apollodorus crater, nicknamed the Spider, due to a network of radiating troughs. However, detailed analysis shows that the crater is not at the center of the faults, and may have formed later. The nature of these depressions remains one of Mercury's mysteries. Another notable crater, named Rembrandt, is second in size only to the Caloris Basin, with a diameter of 715 kilometers. It appears to be a relatively young feature, and likely formed during the period of intense bombardment about 4 billion years ago. The Rembrandt crater stands out with a unique system of concentric and radial ridges and troughs, resembling a spoked wheel pattern, unparalleled on any other celestial body. Remarkably, craters on Mercury are named after prominent figures in the arts. It is particularly pleasing to note the Shevchenko crater, discovered in Mariner images and approved by the International Astronomical Union in 1976. This crater, 143 kilometers in diameter, is one of the most interesting formations on the planet. Despite the predominant grayish-brown hue of Mercury's surface, traces of past collisions create diversity in the landscape. These are the bright streaks surrounding craters, known as crater rays. The colossal energy released during an impact not only forms the crater but also pulverizes rocks. Some of this material is ejected beyond the crater and settles as bright rays. Fine rock particles reflect sunlight better, but over time, the rays darken under the influence of solar wind and dust. Similar bright rays can also be observed on the Moon, where they are more common due to lower gravity, allowing debris to spread further. An unexpected discovery on Mercury was the presence of water ice. Despite its proximity to the Sun, this is possible due to the planet's small axial tilt, only 0.034 degrees, which eliminates seasonal changes. The planet's poles are not illuminated at a direct angle, so ice can persist in craters and permanently shadowed areas. Its first signs were detected through radar observations by the Arecibo Observatory, and later confirmed by the Messenger mission, which found ice in 3 large craters at the North Pole. The origin of the water remains a subject of debate. It may have been delivered by comets, released from the planet's interior, or formed from the interaction of hydrogen ions, carried by the solar wind, with oxygen on the surface. However, the presence of long, winding cliffs, reaching hundreds of kilometers in length, and up to 3 kilometers in height, is no less intriguing. These structures formed as the planet compressed due to the cooling of its massive core. The reduction in the core's volume leads to the compression of the crust, forming wrinkled ridges and faults. The crust, under the influence of gravity, adapts to the shrinking internal space, tearing and pushing upward, creating features similar to Earth's thrust faults, normal faults, and folds. The Discovery Ruby Scarp, reaching 550 kilometers in length and 1.5 kilometers in height, is a prime example of this process. The deformation of crater walls and floors indicates that it occurred after their formation. The Messenger mission discovered faults no older than 50 million years, indicating Mercury's ongoing tectonic activity. The planet continues to cool and contract, leading to the formation of new faults. It is estimated that as a result of this process, the planet has shrunk by approximately 7 kilometers. Mercury quakes, caused by seismic activity along the faults, likely also occur on Mercury. On the Moon, seismometers installed by Apollo missions recorded tremors up to magnitude 5 on the Richter scale. However, given the size of the faults on Mercury, it should shake significantly more intensely. Thus, Mercury remains warm enough to continue contracting. The existence of Mercury's magnetic field, first detected by Mariner 10, serves as strong evidence that the planet's interior still retains significant heat. Theoretical models assert that magnetic fields arise from a planet's rapid rotation and the presence of a molten core. However, considering that tiny Mercury completes one rotation on its axis in 59 Earth days and its small size, its core should logically have cooled long ago. Nevertheless, Mariner's data indicated the existence of a magnetosphere, similar to Earth's and oriented along Mercury's rotational axis. Initially, astronomers hypothesized that this magnetic field might merely be an echo of past core activity, a trace, in magnetized rocks. However, the Messenger spacecraft confirmed that the field is dipolar, meaning it has north and south poles, and is generated by the same principles as Earth's. Furthermore, the planet's crust shows no clear signs of remnant magnetism. Therefore, Mercury's iron core must consist of solid and liquid layers, the rotation of which generates the magnetic field. This internal heat is possibly released through tidal heating, caused by Mercury's eccentric orbit, which periodically brings it closer to and farther from the Sun. As for the atmosphere, Mercury practically lacks one. Practically, because Mariner's data only indicated the presence of an extremely thin exosphere. An exosphere is characterized by such a low density of molecules that they practically do not collide with each other. For comparison, Earth's exosphere begins at an altitude of over 500 kilometers from the surface, which is above the orbit of the International Space Station and roughly corresponds to the current orbit of the Hubble Space Telescope. In contrast, Mercury's exosphere begins directly at the surface and contains various chemical elements, such as hydrogen and helium. These elements likely originate from the solar wind and are briefly trapped near the surface, perhaps for only a few hours, before continuing their journey away from the Sun. Atoms of other elements, such as oxygen, sodium, potassium, and calcium, likely originate from the planet's regolith and are ejected by impacts with meteoroids or by solar wind particles. Interestingly, when the solar wind reaches the exosphere, it strips away some of its atoms and forms a long and spectacular tail, similar to a comet's. Because sodium atoms efficiently scatter yellow light, this enormous tail can be seen with special filters, although it is virtually invisible to the naked eye. Mercury's core represents one of the planet's main enigmas. It is colossal in size, 4,000 kilometers in diameter, which accounts for about 85% of the planet's entire diameter. This fact challenges existing planetary formation models, as it is difficult to imagine how such a massive core could have accumulated without proportionally increasing the planet itself. Conclusions about Mercury's internal structure were drawn from numerous measurements taken using various methods. The Messenger spacecraft, during close flybys, detected slight variations in the planet's gravitational field, allowing scientists to understand how mass density is distributed within it. Ground-based radar observations enabled astronomers to study Mercury's rotation in detail, revealing what are known as librations, slow oscillations of the planet during its movement around the Sun. These observations showed that the planet's mantle is not rigidly connected to the core. By correlating this data with the presence of a magnetic field, scientists formed the modern understanding of Mercury's internal structure. It is believed that the planet has a solid crust and mantle, composed primarily of silicate rocks, similar to Earth. The mantle surrounds a solid outer core layer, consisting of iron sulfide. Beneath that is a layer of liquid core, and even deeper, the planet's inner solid core. Thus, Mercury, composed mostly of iron, is the second densest planet in the solar system after Earth. The question of how tiny Mercury managed to accumulate such a massive core remains one of the solar system's greatest mysteries, one that scientists have grappled with for decades. One of the most interesting hypotheses, as is often the case, is related to the giant impact theory. Perhaps, in the distant past, Mercury experienced a global catastrophe similar to Earth's collision with the hypothetical planet Theia. As a result of this collision, the planet's outer rocky layers might have been lost, leaving behind a metal-rich planetary core. This, incidentally, also explains why Mercury's orbit is so elongated. However, The impact idea was questioned after the Messenger mission, which discovered high concentrations of elements like potassium and sulfur on the planet's surface. If such a collision had indeed occurred, the high temperatures generated would have simply stripped the planet of these volatile substances. A more plausible explanation is that, for example, the Sun's magnetic field might have played a role. In the early days of the solar system's formation, iron particles could have been drawn through dust and gas by the Sun's magnetic field, so planets forming closer to the Sun should have accumulated more iron. According to the authors of a 2021 study, this is why Mercury, Venus, Earth, and Mars have different proportions of metal and rock. Mercury's iron core constitutes almost 2/3 of its mass. Earth and Venus's cores are 1/3 of their mass, and Mars's core is less than 1/4 of its mass. Thus, researchers believe that the density and percentage of iron are closely related to the strength of our star's magnetic field. However, to confirm this hypothesis, at least one more planetary system similar to the solar system needs to be studied. In reality, there are many hypotheses, but none yet provide a definitive explanation for the strange internal structure of the first planet. It is abundantly clear that Mercury, the closest planet to the Sun, urgently requires deeper and more comprehensive study. Currently, the only active mission targeting this iron planet is the ambitious project named Bepi-Colombo. This international initiative, combining the efforts of the European and Japanese space agencies, launched in 2018 and is expected to reach Mercury's vicinity in 2025. The Bepi-Colombo mission consists of 2 separate spacecraft, each performing its unique task. After a long and complex journey to the planet, these spacecraft will separate and enter different orbits around Mercury. This will allow for the collection of an unprecedented amount of new information about the planet, unveiling many of its mysteries. The European spacecraft will focus its efforts on a detailed study of Mercury's surface, examining its geological features and composition. The Japanese spacecraft, in turn, will investigate the planet's magnetosphere, studying its interaction with the solar wind and its influence on the surrounding space environment. In 2021, the Bepi-Colombo mission successfully completed its first gravitational flyby of Mercury, allowing for the first images of the planet's surface to be obtained. This historic moment made Bepi-Colombo only the 3rd spacecraft in history to approach Mercury and capture its appearance. After entering its planned orbit around the planet, the mission is designed to operate for 1 year, although there is a possibility of extending it for another year. It is important to note that space technology must function in extremely harsh conditions, exposed to intense solar radiation and extreme temperatures. Therefore, the relatively short mission duration should not be surprising. It is worth mentioning that the Messenger mission, Bepi-Colombo's predecessor, was also designed for 1 year but operated for a full 4 years, exceeding all expectations. In any case, if all goes according to plan, Bepi-Colombo has every chance of becoming the mission that will finally unravel the mystery of Mercury's core and other key features of this enigmatic planet. As a result, Mercury may lose its reputation as the most mysterious planet in the solar system, yielding to other, as yet unexplored, celestial bodies.